This is an update on the Twerk Lidar robot project. At this point, I was able to figure out which way is down by following this video from Matlab. It was really hard to figure out how to use an IMU. I read a lot of papers and whatnot, and ultimately this video was the most helpful thing. I've got that linked below. But I want to point something else out. The gait you're seeing here as it walks, it's not mine. I had to look at some people's videos on how they walk, because originally when I programmed mine, the legs were like a perfect mirrored X, and I didn't realize, since it's statically balanced, I'm not using the IMU to shift the center of gravity around as it's lifting a leg. So there's always 3 legs on the ground anytime, and it's in a specific triangular shape. But yeah, and then after that I've been figuring out angular velocity from the gyro, so I can tell the sweep and pitch angles. So here you can see, well, back there you saw that the thing's running into things, and that's the whole point of this project, is it has to have a brain. And yeah, so it's not going to be anywhere near as good as a spinning LiDAR or a computer vision thing. I mean, it's a single point, and you just swing it around and find things. And mostly the thing I've been finding is the measurements are not good. You can see here how it's shifting around. Yeah, that's not good. That's because the outer legs don't move, and also in this video the gaits weren't matching end to end between the default standing position of the servos and then the sweep pattern, so I had to update that. Right now the pitch positions are also messed up. So yeah, I'll just go over some of the things. So here I've got a 3JS web interface. It's receiving the 9 values from the IMU, the raw values. So right here the green axis is down, and you can see when I tilt the robot and point it away from me, the green axis goes that way. And then I'm computing the NED coordinate frame, northeast down, which that Matlab video talks about. So with this I can tell which way is down, which seems simple, use the Z acceleration value. But the only thing is, when I hold it in my hand, I'm okay, this is ways down. If I tilt it that way, the axis should point that way. But the other axes are flipped. I can't guarantee which way they go, so I don't know what's up with that. Also, this data streaming thing is not working well right now. I found a WebSocket library for the ESP, and in the past it was good enough to just send forward for manual remote control, but streaming data, there's a problem where the serial buffer builds up, and then it loses sync between the teensy main loop. So I don't know. So the yellow here is the pan tilt sample area. So far I'm going with 25 left to right, and then 15 degrees up and down. And then the red thing is an object that's in the sample area, and then you'll get something like this, which is the item. And then all that would happen is you would track this as a solid box to avoid relative to the robot. This is an example pan tilt data set. I'm syncing everything by the Millis function library, I don't know what you call it. But it's a clock epoch kind of thing, where it just keeps counting up. Epic. But yeah, so these are the raw values from the gyro. So I converted it to degrees per second, and then these samples are approximately 0.029 seconds apart. And then you just sum that, and then you get the angle that it should have moved, which it's somewhat accurate. Like the geometry doesn't make sense. Like the servos are in an X pattern. Let me see if I can pull it up real quick. Here. So, oh my god, hold on. So these are like that, and when it sweeps, it turns the servos right now at 50 degrees. It was 30 before. So like this one goes this way 30 degrees, that one goes that way 30 degrees. And I would think that the entire thing, like from here to there, rotates 30 degrees, but it doesn't. It only rotates 15. And I'm like, how does that make sense? But that's what the gyro was measuring, and I didn't believe it at first, and then I proved it with a external recording. Same for the pitch. So, I filmed it pitching, and then I took some measurements in SketchUp, and yeah, they weren't matching the servo movements. But it's neat that it's close. Right now, the pitch values are not accurate. They're supposed to be like 9 degrees or something, but I'm only getting like 4. But yeah, so that's how I will tell like where the beam is pointing at the time. And then these are the distance measurements from the time of flight sensor. They're in inches. And then the robot is like a 8.5 inch cube, pretty much. So with that kind of info, you can navigate the world. But we'll have to see, because the math is not 100%, and the sensor accuracy, and if there's like a weird irregular shape and the thing completely misses it, that's the bad thing. Overall, though, I'm pretty happy with the project. I mean, it's a lot better than this previous one. This one, it was just like a bump sensor. I had no idea about the world, but yeah, the hexapod thing is different too. This one wasn't a true hexapod, but yeah.